Welcome to springlib.
Hi everyone, so what we have here is the pilot of an airplane that's executing a vertical loop that follows the path of this function shown here, that r is equal to 200 times 1 plus cos theta. We know the velocity of the pilot is 85 meters per second and that the mass of the pilot is 80 kilograms. What we're asked to solve for is the vertical reaction force from the seat on the pilot during this loop. So the way we're going to be going about doing this problem is utilizing our knowledge of normal, tangential, and basically rotational motion, and using a free body diagram and combining those two with Newton's second law to develop our equations of motion and solve for this force. So let's go ahead and get started. So what we're going to do first is calculate the first and second time derivatives of r. So we know that r is equal to 200 times 1 plus cos theta. And we can see that r dot is equal to 200, or basically negative 200 sine theta times theta dot. Then we know that r double dot is equal to negative 200 times the quantity cos theta times theta dot plus sine theta times theta double dot. Then what we can do is we can say that when theta is equal to 0 degrees, we can see that r is just going to be equal to 400 meters. R dot will be equal to 0, and r double dot will be equal to negative 200 times theta dot squared. Now theta dot for us currently is an unknown, but using the knowledge of velocity that's given to us and our relationship with velocity in normal and basically in radial and rotational motion, we can solve for this theta dot. So we know that v is actually just equal to the square root of r dot squared plus r theta dot squared. So we know v, so we can therefore say that v squared is just equal to r dot squared plus r theta dot, the whole squared. Isolating this for theta dot gives us that theta dot is just equal to 0.2125 radians per second. Now we can solve for this because we know r dot is equal to 0 and we know v squared, which is given to us, is 85 meters per second. Next, what we can do is we can go ahead and solve for acceleration in the radial direction. We know that ar is just equal to r double dot minus r theta dot squared. This gives us that ar is equal to negative 27.09 meters per second squared. Next, we can draw our free body diagram of the pilot. So here's our pilot. Here's the theta direction, and here's our r direction. So here's our weight force, and here's our normal force that is also acting opposite to it. So from this, we can develop Newton's second law in the r direction and say that the net force in r is equal to m times ar. And we can see that this will simply just be equal to weight minus the normal force is equal to m times ar. Isolating for n gives us that w minus mar is equal to n, and this gives us a normal force that's equal to 2.95 kilonewtons. And that's our final answer.